Hi, this is Professor Greg Smith from the Department of Applied Science at the College of William & Mary and the Neuroscience program here at William & Mary. I've gotten good feedback on working through homework problems on this screencast-o-matic format. We're going to try it again. The problem that we're going to work on today is to sketch the phase plane, do a little phase plane analysis for the two-dimensional nonlinear system of ODEs that you see in the upper left. So this is the rate of change of x is equal to x minus y minus x cubed here, and the rate of change of y is equal to x. Now usually the best way to begin in phase plane analysis is to draw the alkalines, and in this case the y alkaline actually looks simpler, so I'll start with the y alkaline. Alright, the condition for the y alkaline is that the rate of change of y is 0. So this is the condition that actually determines the location of the y alkaline. Any pair of points x, y in the plane that satisfies this condition is considered to be part of the y alkaline. Now this condition pretty obviously implies that x is equal to 0, because if I set y dot equal to 0 on the left hand side of the second equation, we get that 0 is equal to x. So the set of points in the plane that are on the y alkaline all satisfy this equation, x equals 0, and that corresponds to a vertical line, which I'll sketch in on the phase plane. Still getting used to my pad, so some of these lines might not be as straight as we would like, but that's the y alkaline. So now, what about the x alkaline? Well, the x alkaline satisfies this condition that x dot is equal to 0, and x dot being equal to 0 gives us a slightly more complicated expression than previous. It's 0 equals, and then the right hand side of the first equation, x minus y minus let me do this a little better, minus x cubed. Alright, now in order to plot the set of points that satisfy this condition, it's probably easiest to move the y to the left-hand side. So the set of points we're interested in satisfy y equals x minus x cubed. Okay, so this will be a cubic function that when x is very large, this function is very negative. So it's going to have to start up here, go down, up, and down again like this. I guess to graph it, why don't we note that I can factor the left-hand side to be x times 1 minus x squared. So that means that this cubic function that we're trying to draw needs to cross the horizontal axis, the x-axis, 3 times, once when x is 0, and once when x is negative 1, and once when x is positive 1. And now I know that the function has to be a decreasing cubic function, so I will attempt to sketch that in now. Here's the first crossing of the horizontal axis, the second crossing of the horizontal axis, and the third. So what next? Well, maybe one thing that we should remember is that the flow across the x-null-cline must be moving in the vertical direction. So, for example, imagine that there was a solution that was at this point on the x-null-cline. The x-null-cline, the definition of the x-null-cline is the rate of change of x is 0, and that means we can't move to the left or to the right. So if we were to leave this null-cline, we would have to leave either upwards or downwards. So I can indicate that by putting a hash mark, vertical hash mark. And this is just to remind me that if I'm going to draw a trajectory, solution of the differential equation, and it's going to cross, if such a trajectory crosses the x null-cline, it must do so in vertical direction. And similarly, the y null-cline, if it's going to be crossed, must be crossed in the horizontal direction. Now, I know a little bit more than this. I can actually figure out whether the flow is going to be moving to the left or to the right across the y null-cline, moving up or down across the x null-cline. And let's do up and down first. That seems to be easier in this problem. Y dot is equal to x, so that means that the rate of change of y always has the same sign as x. So if x is a positive number, which it would be, to the right of the y null-cline, the rate of change of y is positive, which means that y is increasing. So I actually know not just that the solution is going to go vertically or in some, or up or down. I know that it's going up across the x null-cline. In a situation where x is positive, and if x is negative, and I were to cross the x null-cline, I would have to move downwards. And a similar argument tells us that if y is large enough that we are above the cubic, that y will actually be decreasing. Now, this is a little bit more subtle, but if you look at the right-hand side here, you could rewrite that as x minus x cubed, and think of this as a quantity, and then subtract y afterwards. And so you can see now that if y is greater than x minus x cubed, that this expression, the difference, will be negative, so the rate of change of x is negative. So this expression is negative when y is large, when we're above the cubic, and that would mean that the flow has to be going to the left above the cubic, and it has to be going to the right below the cubic. Now, there's other ways of indicating this. You can consider a point out here and note that since x is positive, the rate of change of y must be positive, and since we're above the cubic, the rate of change of x must be negative, and then that would tell you that in sort of this quadrant, the flow is generally to the northwest. And a similar logic would get you to draw arrows in the following way here. Ultimately, we know the flow has to go in this direction, and then in this direction. In this quadrant, it's generally in that direction. But So it's sort of your preference in terms of how you would do this. I think that I'll just leave all these arrows on, maybe just erase that piece there. Now, what else can we do? How many steady states does this problem have? Well, a steady state is someplace where in the plane where the rate of change of x is 0 and the rate of change of y is 0. That means a steady state has to be located on both null lines, and I see only one intersection of these two null lines, so that the origin is evidently a steady state. So we have one steady state, and we can think of that as the ordered pair x ss y ss equals 0, 0, the origin. Now, it's probably a good idea to check that if we plug in 0 for x and 0 for y into the original equation, that we get that the rate of change of x and y are both 0, and that's pretty obvious because 0 minus 0 minus 0 is 0, and if x is 0, the rate of change of y is also 0, so that is indeed the steady state. Now, in order to determine whether this steady state is stable or unstable, requires a little bit of analysis, and so we could do that next, and that would require us to take some partial derivatives of the ODE model, which allows us to write down the Jacobian for this system, and then we could evaluate the Jacobian at the steady state. But why don't we stop here for a moment and just confirm that our phase diagram is more or less correct by putting these equations into p-plane and seeing if we get something similar. So I am going to open up p-plane. And here's the p-plane equation window, and I've put our model equations in and chosen some minimum and maximum values for y that work, and now I'm going to graph the phase plane. Now what p-plane does initially is simply calculate the direction field for various locations in the plane. Let me get everything arranged here nicely. Okay. And now what we could do is just ask p-plane to show us the null lines and the direction flow. So I'm going onto the menu here, which you can't see, and I'm saying solution, and then show null lines with arrows. And you can see that we pretty much got it right. Now I'm going to click on several locations just to sort of see what the solutions might look like. And there is an example solution there, which in forward time, and I can tell forward time by the direction of these arrows, is crossing the vertical null line and then crossing the cubic null line, and then wrapping around the sort of knees of this cubic equation, and this solution eventually converges asymptotically to a limit cycle, and that's one of the types of steady state solutions that we can get, steady state periodic orbit.